what I'm going to do in the rest of this lecture is on the PowerPoint, which I should have given you a handout out, right? So you should have got one of these. This is explaining two different topics, but things related to what we did last time. So let me explain what they are. If you remember last time, we had the equations of an ideal gas, right? PV equals NK Boltzmann T, and U is equal to NCV T. These were the equations of an ideal gas. Firstly, I said instead of using the number of particles, you can use something called a mole. So you could write, for example, the first equation as equal to the number of moles times something called the molar gas constant times the temperature. Okay. And for example, the number of moles is the atomic weight of the substance in grams. So if you've got hydrogen gas, which has a molecular weight of 2, then 1 mole of hydrogen gas will be 2 grams. So in order to do this, you need to know how many particles are in a mole. Okay? So I said that the number of particles is equal to the number of moles times the number of particles in a mole. And this thing, Na, is called Avogadro's constant, or Avogadro's number. So the first topic of the presentation I'm about to show you is how do you measure Avogadro's number? In other words, how do you count how many particles are in 2 grams of hydrogen? If I have 2 grams of hydrogen gas, how do I count how many molecules there are? Okay? Obviously, you can't just count them directly because there's no way you can see them. So you have to use indirect methods. That's the first point of the presentation. The second point of the presentation concerns this thing, CV. For example, I told you that for a monatomic gas, you find that CV is almost exactly 3/2 times the Boltzmann constant per particle. Okay? And there's a reason for this. This is known as something called the Equipartition Theorem, which explains why the heat capacity of a monatomic gas looks like this. Okay? So those are the two topics of the presentation. First of all, how do we measure Avogadro's number? And secondly, how do we theoretically calculate the heat capacity? Okay, so Avogadro's constant is named after this guy, which is Avogadro, possibly. Okay. He did not actually measure it. Okay, so it's named after him not because he measured it, but he was the first person to use the idea that the ideal gas law looked like this to suggest that we could write a mole in terms of a constant number of particles. Okay. So he came up with the idea of this constant, but he didn't actually measure it. That was done later on. Okay. Okay, so this explains what we saw last time. You can write the ideal gas law in 2 different ways. Firstly, like this, in terms of number of moles, molar gas constant. And secondly, you can write it in this way in terms of the number of particles and the Boltzmann constant. But in order to go between them, you need to know how many particles are in 1 mole. Okay? This is Avogadro's number, and this is what you need to calculate. Okay. So it's been calculated in lots of different ways. I'm just going to explain one way in which it has been calculated. It's not the first, and it's not the most accurate, but it's one of the more interesting ways that you can calculate Avogadro's constant. And this method relies on first knowing the value of charge of a single electron. Okay? So if you know the charge of an electron, you can measure Avogadro's constant. So first of all, we need to explain, how do you measure the charge of an electron? This was done in what's known as the Aldrop experiment, which was performed in 1909. And it works in the following way. You have an oil can which sprays very small spherical particles of oil into a box. Okay? So this sprays very small and therefore spherical particles of oil into a box. Now, on the way out, because of frictional forces, some of these particles will become charged. So as the oil comes out of the nozzle, I've got little bubbles here, they become charged. Okay? Some of them become charged. And in particular, they pick up a negative charge, which can be different depending upon the molecule. So as a result of frictional forces, some of them pick up a negative charge. Okay. Now, because of gravity, these oil droplets will fall. Right? They fall. But if you imagine that you're falling, if you're a skydiver or something, you fall because there's a force of gravity called, well, which we call G, 10 meters per second squared, right? Which pulls you down to Earth. So initially you fall with a constant acceleration. But as you fall, there's another force, which is because of air resistance, which tries to push you back up. Right? If you're falling through the air, then the air rushing into your face tries to push you up. Now, this size of this force is dependent upon how fast you're falling. So if you wait long enough, you will eventually reach a stage where the force of gravity is exactly equal to the resistance force from the air. And in this case, your velocity is constant. So you fall, you start to accelerate with g, but then you slow down accelerating because of the resistance force, and eventually you reach a constant velocity. Okay? This is known as the terminal velocity. Okay. Now, people have a very high terminal velocity, and if you jump, it will take you a long time to reach the terminal velocity. Right? But these oil drops, because they're very small, they have a very low terminal velocity. So if you spray oil into the air, it will fall at a roughly constant speed and quite small speed downwards. Okay? So these oil droplets reach constant velocity. And in particular, for the case of small spheres, it's well known that the resistance force is, to a very good approximation, proportional to the velocity. So the resistance force is proportional to the velocity. So you fire these oil droplets out. Some of them become negatively charged, and they fall and they reach terminal velocity, which for an oil droplet is pretty slow. So they fall slowly. Okay? So they go into this box, they fall down. Some of them go through this very small hole, which you can see here. Okay? Most of them just hit the floor, but some of them will fall through this hole. Okay? And through this hole you put a microscope so you observe the oil droplets falling through this hole. Okay. So this is an enlarged diagram of that on the right. Here's an oil droplet. You're watching it here, so you watch it fall. Okay. And it falls at a roughly constant velocity. Okay. Now, by measuring how fast it falls, the equation is here. The force of gravity should be equal to the resistance force. So by measuring how fast it falls, you can measure this constant alpha. Okay? Now the next bit is the clever bit. After it falls, you turn on an electric field, like this. Okay? So if you turn on an electric field, this particle is negatively charged, right? Negatively charged. So if the electric field is going this way, down, the particle will feel a force going up. So, you let it fall through gravity first, measure the constant alpha, turn on the electric field, and then it goes up because of the electric field. And then in this equation, you know everything. You know the mg, because you measure it as it falls. You know alpha. You know the electric field strength E, and therefore you can calculate what is the charge of the oil droplet Q. So by measuring the difference in speeds, first as it falls under gravity, and secondly as it rises under the influence of an electric field, you can determine the charge on the oil droplet. Now if you drew this, and you plot a graph of what's the charge of each oil droplet, you don't find a mess of possible values. You find, in fact, that there are only certain values that Q can take. So you find a lot of particles here, a lot of particles here, here and here, and so on. Okay? But the distance between the charges is fixed. And the way you interpret this is one oil droplet may have a charge of 1 electron. The next oil droplet may have a charge of 2 electrons. Okay? And then you may have an oil droplet with a charge of 3 electrons and 4 electrons and so on. So by measuring the size of the gap between the charges of different oil droplets, you can determine what the charge of 1 electron is. The oil droplets are charged because they have a certain number of electrons. Okay? Therefore, the charge of the oil droplet comes in units of the electron charge. So by measuring the charge of the oil droplets, you can determine the electron charge. Okay, so that's how you measure the electron charge. Once you know the electron charge, it's quite easy to measure Avogadro's constant. So this is one way you can do it. This is known as an electrolytic cell, which hopefully you've seen before. So you have a half circuit, battery here, current flowing around this way. You attach it to 2 metal rods, which are known as cathodes. Let's say they're made out of copper, in this example. And then you put these cathodes into water. Now, because water is a poor conductor, usually, that means the current flowing through the water will be very small, because water doesn't conduct electricity very well. However, if you dissolve a salt into the water, and in this example we've dissolved the salt, which is copper sulfate, that's CuSO4, then in the water that separates into copper ions and sulfate ions. Copper ions are positively charged, +2, and sulfate ions are negatively charged, -2. Once you put the salt in the water, you can get an electric current flowing in the following way. The electrons will be driven by the battery down into this electrode called the cathode. Okay? Once they are here, the negative charge on the cathode will attract copper ions from the solution. So copper ions from the water will move onto the cathode, okay, and absorb the electrons. At the same time, the sulfate will be attracted to this positively charged anode, as it's known, and the electrons from the sulfate will return to the anode and flow back around the circuit. So you have a completed circuit now. Electrons go here, are absorbed by copper, and then the electrons from the sulfate ions come here and travel around the circuit again. So in this way you get a complete electric circuit. Now as you run this experiment, you find that the cathode becomes heavier. Right? Because each time 2 electrons go around the circuit, 1 more copper ion is absorbed. So the number of copper ions absorbed onto the cathode is equal to the number of electrons divided by 2. Right. So given this, you can find Avogadro's constant as follows. As the current flows, copper is attracted and deposited on the cathode. Its mass increases. So you wait until the mass of the cathode increases by 1 mole. Now for copper, I think that's about 64 grams. So you wait until the mass of the cathode increases by 64 grams. You know that's 1 mole of copper. Okay? At the same time, you measure the current flowing around the circuit, and therefore you can calculate the total charge which has moved around the circuit. That's equal to the current times the time. Because you know the electron charge, you can work out how many electrons have flown around the circuit. The number of electrons is equal to the total charge divided by the charge of 1 electron. So you know how many electrons have gone round. And you know that for each 2 electrons, you get 1 copper atom. So the number of copper atoms that have been moved is equal to the number of electrons divided by 2. So you wait until this increases by 1 mole, you measure the charge, calculate the number of electrons, calculate how many copper atoms have moved. And in this way, you can come up with the correct answer, more or less. The Avogadro's constant is about 6 times 10 to the 23. So it takes 6 times 10 to the 3 copper atoms to make 63 grams of copper, 64 grams of copper. So notice that no time did you have to look at an individual copper atom. You can do it all by indirect methods. Okay, so that's the end of the first part of the presentation. This is how Avogadro's constant is measured. Now let me explain the second part. So this is the Equipartition Theorem. This is about telling you what should the value of the heat capacity be. Now, the theory of statistical mechanics, which is what I'm going to talk about in the second half of this course, has a prediction about the heat capacity. And the classical theory, we can state it as follows. If you write down what the internal energy of the system is, you will find that there are some variables which appear in the internal energy as squares. For example, in the monatomic gas, the energy of the gas is just the sum of the kinetic energies of each particle in the gas. Right? So the total energy of the gas is the sum of a half mv squared, and v squared is made up of vx squared plus vy squared plus vz squared. So in the energy, there are 3 variables which appear squared in the energy. This equipartition theorem says that for each variable which appears squared here, you get half